So good morning, everybody. It's a pleasure to be here and to get to share a little bit about the work that people in my group do and some people here at the University of Waterloo do. Um, so I'll give you the punchline to start off so that you can keep that in mind and you don't need to worry about it later. We're going to be looking at how quantum probes, or talking about how quantum probes can be used to understand and quantify and describe space-time. And so we'll have simplified quantum systems. We've heard about qubits, two-level quantum systems, and we're going to be describing space-time in terms of general relativity ideas and describing how these two can be coupled in a way that we can measure this part and infer information about that part. And so the takeaway, if you don't remember anything else from this talk, I want you to remember that qubits can be used to learn about quantum properties of gravity or about quantum gravity. Now, to kind of set the stage, I want to go back about 100 years when there was a revolution in physics. And instead of it being liberty guiding the people against the monarchy, we had Albert Einstein guiding people against the ideas of absoluteness that prevailed in the physics community of classical physics at the time. And by his side were the ideas of relativity and the idea of uncertainty. And specifically, relativity was kind of described by his theory of general relativity, and the uncertainty was featured in ideas of quantum mechanics that were being developed at the time. And these two parts of physics that were developed about 100 years ago form really the pillars of modern physics. So if you're in your early undergraduate career, you might have taken a modern physics course that focuses on these two areas of physics and how they've kind of changed the way we talk about physics nowadays. And they're very distinct in the sense that GR talks about the large scale and is deterministic, so cosmology, astrophysics, how planets move, satellites, all that sort of stuff. Whereas, as John's pointed out, quantum physics was developed to describe small scale, and it's inherently probabilistic. So these two theories have been incredibly successful, have had lots of applications, and yet there's a bit of a gap between them conceptually. And that gap's actually even worse when we look at the foundational ideas, because in general relativity, a big idea of this relativity component is that different observers see different physical processes happening from their perspectives. And on the quantum case, it's not even clear what an observer is. There's a lot of debate about who's seeing what. If you've heard about Schrodinger's cat, when is the observer this? Where do we distinguish between the observer and the system? So bridging this gap is something of interest because as physicists, we're always trying to come up with a more fundamental understanding of the world around us. And we know these two things work, but how do they work together? And that's one of the big questions of physics in this century. And it's a very hard question, one that has not had a whole lot of progress over the last 100 years. And I'll note there are some exceptions. The one I want to draw your attention to is the idea of quantum field theory. This is tremendously successful, used to describe a lot of quantum properties or a lot of quantum physics nowadays. It doesn't really use the whole GR generally. Normally, it limits itself to special relativity. So there are some relativity considerations, lots of quantum, but there are still some caveats even in this theory. And the result that I want to highlight is Hawking radiation. So maybe by quick show of hands, who here has heard of Hawking radiation? OK, this is pretty good. Terrific. Yeah, so what is Hawking radiation? Well, it came out about 50 years ago in this sensationalist titled short article. It's 2 pages. You can read it by Hawking that popped up in Nature. And kind of the setup is quantum field theory with some elements of curved spacetime, some elements of GR. There are some approximations. So it's not in and of itself a full theory of quantum gravity, but it's a really good first step. And what he realizes is that black holes have temperature when you account for quantum properties near black holes. And this temperature is written here. This is his not tombstone, but I think it's in Westminster Abbey. You're famous enough and you do cool enough things, and in the UK, you get your own little tile. Or it looks like he's got 4 tiles, actually, in Westminster Abbey. And when this came about, people started asking questions like, well, how might we detect it? And there's like a straightforward physical sense in which you can measure things, using telescopes and satellites in the sky. But more fundamentally, how would we detect this quantum phenomena? And there's actually a Canadian who was at McMaster at the time, now he's at UBC, Bill Unruh, who created and described how we could use particle detectors, not the kind that you hear about at CERN, the huge things that take a bunch of data and use AI, but something much more simple, a qubit, a 2-level system, a ground state, an excited state. And when you detect the radiation from the black hole, your qubit can go from its ground state to its excited state. And if you have many qubits, you can infer statistics about this and reconstruct and learn information about the black hole just by measuring these quantum systems. And in particular, you can use the tools from quantum information to do this sort of a task. So I'm going to give you a quick sketch of how a lot of problems in the RQI field kind of get set up. Hawking radiation would be one example. At the time, people were talking about information theory, and quantum information was starting to show up in the last 40, 50 years, but it was kind of existing in a separate field. So John mentioned quantum information, those got brought together, and then I'm bringing in the GR component. So the pipeline, if you will, of how a lot of these problems work is that you've got some space-time. It could have a black hole in it. It could also be, because of the analogy between gravitational fields and accelerations and general relativity, you could just have accelerated observers in this case. And you're going to have a quantum field that's coupled to it. And this is kind of what Hawking did, and it's well understood. And Hawking described things at this point. And what we're doing is we're adding this simple quantum system that's going to be probing the quantum field. And then we're going to apply the tools of quantum information that we know really well to understand this system and infer ultimately information about the relativistic properties of our setup. And the hope is that we learn some new insights about how quantum physics and general relativity behave when they're put in the same room together. Now, focusing in on the quantum info side, because we are at IQC and this is a quantum talk, and that's kind of the new thing that is happening in this RQI setting. We're able to leverage, so this book is like just shy of 700 pages. It's, 26 years old now, so it was published in 2000, but people still use it as kind of the go-to first stop for understanding quantum info. There have been some developments since, but it's really good, and it'll tell you all about qubits, quantum gates, and quantum protocols. So we can use these ideas to, such as actually properties of kind of the highlight, the hallmark property of quantum systems is quantum entanglement. But since people talk about all sorts of other cool things, contextuality, et cetera, and we can use these properties to understand things about how space-time affects quantum, how relativity affects quantum. So I'm going to give you 3 kind of case examples of how kind of the highlights of RQI research and what we've been able to learn, from using these quantum information tools applied to this relativistic setting. So the first, this was developed 20 years ago. Actually, my supervisor was one of the people on this paper, or a series of paper, and it's the idea of entanglement degradation. So if you have a quantum system in the presence of a black hole, or if you're accelerating it through space-time, the entanglement's actually going to decrease. And there's all sorts of reasons why entanglement's hard to maintain, even in our everyday life. But there's a gravitational effect that contributes to this. It's not a real concern for people building quantum computers here on Earth. The gravitational field's not that strong. There are other problems that are much more pressing for building these quantum computers. But fundamentally, understanding how these two systems interact is important. More recently, there have been some developments in terms of studying how entanglement harvesting can be achieved. That is, starting with a system that has no entanglement, coupling it to the quantum field, and extracting that entanglement. So you're not creating entanglement, you're transferring it. But in essence, you're bringing it into a system that you can access from a system that you couldn't. And there are gravitational implications on this. So different spacetimes, different trajectories can enhance or degrade the entanglement that you're extracting from the field. So here we start with initially entangled states, and we see that it degrades. And here we're starting with non-entangled states. We're generating that entanglement. And lastly, and maybe most exciting for me as somebody who is interested in trying to understand quantum gravity, is a proposal that came out 10 years ago by a group led by Sugato Bose in the UK, and then Chiara Marletto and Vlatko Vedral in the UK as well. And it's the idea of gravity-induced entanglement. So we understand entanglement in the quantum sense. But this proposal is an experiment where if you can superpose a mass near a test mass, if gravity is quantum, that test mass should also find itself in a superposition. So what you've done is you've entangled two masses. These are going to be microscopic masses. If you can entangle these two masses and with confidence state that the only interaction between the masses was gravitational, so there's no other standard quantum system interacting the two, then you can state that gravity must be quantum because we've measured quantum entanglement between gravitationally interacting systems. And people are really trying to advance this, this research, and we'll see where it takes us. So before I finish, I just want to plug, John mentioned the International Year of Quantum. There's actually a magazine that came out showcasing all sorts of cool articles about this. You can read the one on RQI that I helped write by scanning this QR code. It's also on the next page. And then you can go read all the other cool articles about the quantum tech happening in Canada. So with that, I'll leave you with the takeaway message that qubits can be used to learn about quantum gravity. And we have a bit of time during which I can answer a few questions. Thank you.
Yeah, so we do have just about 2 minutes for questions. Raise your hands.
Yeah, so you mentioned that when you mentioned Hawking radiation, you mentioned that how it's like one of the biggest barriers to like RQI. Can you like be a little more specific as to like how it's a barrier and like how Hawking radiation or just like maybe black body radiation in general like affects quantum information?
Okay, yeah. So I guess there's two things to disentangle here. The first is how we can use these quantum properties to detect to detect Hawking radiation. So that's not how Hawking did it, but basically we're saying we can use these tools from quantum information to actually have a more physical description of this property. The second component is how does Hawking radiation affect other RQI protocols? And you can imagine, so if Hawking radiation is kind of a black hole sending out a stream of photons, you can imagine if you're doing something else near that black hole, that stream of photons could mess with what you're doing. It would be a source of noise. And there's a relation between that temperature and the mass of the black hole. More generally, you don't need a black hole. You can actually, if you just have acceleration, you get similar effects. But yeah, so it's important you can either have it leverage to enhance your signal, or if you're not careful, it can cause problems and destroy the signal. Thanks.
We have one here.
Yeah.
I know you mentioned that you said that qubits are used to learn about quantum gravity.
Yeah.
How are you creating those qubits, and if so, what kind of qubits are they?
Yeah, that's a great question. So maybe I should have been more explicit right off the get-go that I'm a theorist. Probing black holes is super hard stuff, right? And my supervisor has suggested to us that we go and hop in a rocket and go test some of these things ourselves. Nobody's volunteered. Nobody's signed up for that. We're using, basically, you can think of it as an atom with an electron, and that electron has different energy states. And we are looking at the excitation of that electron to a higher energy state. And that's what we're using to, yeah. Like if you want to imagine it physically, that's the toy picture that I would give you. But yeah, more generally, we're looking at how those quantum tools in theory can be used to understand these quantum systems. I see my time is up. So